Hello everyone, my name is Joseph Williams. This is our CIS 527 Smart Lock Checkpoint 2 presentation, and I'm presenting on behalf of Group 5. So Group 5 consists of myself, Tyler Franks, and Sweta Gandhi. Okay, so here's an outline of what I'll be talking about. I'm going to start with the assumptions we're making for the system, and then I'll spend a little bit of time talking about the functional requirements we need to meet for this project. After that, I'll spend some time talking about the non-functional requirements we came up with. Then I'll discuss the protocol selection process and why we ultimately chose to use MQTT. Then after that, I'll provide some more detail about the MQTT architecture itself. And finally, I'll discuss some of the details of our system design and how we plan to actually implement it. Okay, so here's a list of our system assumptions. First, the lock and the client should be able to communicate bidirectionally through a central broker, and the broker should simply forward messages between the lock and the clients. So client should be able to send commands to the lock, and the lock should be able to send status updates to the clients, and all the messages should pass through a central broker. And then also, the system should support clients within the home network and clients that are outside of the home network through port forwarding. And then finally, our system will not integrate communication with a cloud-based server because we want to avoid the latency we saw in the example smart lock project from the Hacker Shack YouTube channel. So in terms of requirements, first, the client needs to be able to communicate by sending messages to a smart home gateway. The gateway then forwards the messages to the appropriate receivers. Also, it's really important that the system implements some form of authentication so that only trusted users will be allowed to communicate with and control the locking mechanism. This will be implemented through a combination of permanent and temporary passwords. The permanent password belongs to the homeowner and can be used forever. Finally, through the use of temporary passwords, the homeowner will be able to grant a visitor temporary access to the smart lock. One thing to consider is that to avoid a potential security issue, unused temporary passwords must automatically expire, or the system must provide a way to erase them. Okay, so the functional requirements also include heartbeat and status messages. These messages are sent by the smart lock itself to the gateway, so the heartbeats must be periodically sent to the gateway or broker in our case. This will allow trusted clients to monitor the current state of the smart lock. Additionally, if the locking mechanism fails, the clients must be notified. The lock must also publish status messages, and trusted users should be able to view a log of the smart lock state over time. This will include information about what commands were sent and when. Finally, the clients should be notified if the lock is in a broken state. An example scenario might be if the lock reports that its current state is locked, even though the door is open. This means that the smart lock must also be able to monitor the position of the door it's mounted on. So this is a list of our non-functional requirements. So first of all, we want to keep latency as low as possible. So we want to minimize response time, and we want the user to have a good experience when they interact with this system. And so we want to keep the response time below 100 milliseconds, because if you go too much higher above that, it's just going to significantly decrease the user experience. And then we also, if there's enough latency to cause a command to be dropped, we would want the client to be notified, but for our system, that really shouldn't be an issue. And then for consistency, the door status messages, they should be consistent with the actual state of the door. So we don't want some kind of issue where two clients send it once and then the messages are delivered out of order, and the door reports to be in a state that it's not actually in. So we want to have a way to avoid that. And then also, in terms of reliability, we plan on implementing quality of service level 2. And so for this system, we want to deliver at exactly one message, essentially. So we don't need to, if the lock receives a lock or unlock message, it doesn't need to pay attention to duplicate messages. And then finally, because we're actually planning on physically constructing this project and having working hardware, we want to keep the cost of the hardware as low as possible. And so ideally, we want to stay below $100 for additional parts. And so far, we've been able to do that. Okay, so for protocol selection, actually HTTP was my original first choice because I've built a number of RESTful APIs for web applications in the past, so I'm already pretty comfortable with it. However, upon further review, we realized that because HTTP is not designed for IoT projects, it can actually create a lot of unnecessary overhead, and it can have poor energy efficiency. So this isn't good for IoT projects because the hardware is often battery powered and has limited memory and CPU processing power. So incorporating a protocol like HTTP in a project like this really wouldn't have been a good use of resources. So we also considered CoAP. This was potentially a good fit because it's actually energy efficient and has lower overhead than a protocol like HTTP. The downside of CoAP, though, at least for this project, was its lack of quality of service guarantees. So ultimately, we decided to go with MQTT, or Message Queuing Telemetry Transport, and we'll provide some more details about this protocol in the next slide. So first of all, MQTT is a better choice than something like HTTP because it was actually designed for IoT projects. It utilizes PubSub architecture to provide a scalable way to manage many IoT devices. This is good because realistically, you wouldn't want to be limited to just a single smart lock. You might want to include multiple smart locks or connect a whole host of different devices. Also, because it was designed for IoT, MQTT is significantly faster and more power efficient than a protocol like HTTP. And as I mentioned in the previous slide, this is great because IoT devices are often constrained by hardware limitations. Additionally, the small header size and topic sharing improve scalability. Also, MQTT was a good choice for us because it has quality of service guarantees. So, for instance, if we want to ensure that the lock message was actually delivered to the smart lock, MQTT can give us that peace of mind. Another nice feature is last will and testament. This will allow you to store the client's last will in the broker. For example, if the smart lock loses power and stops communicating with the broker, if the broker knows that the smart lock's last will was to notify the mobile phone clients of this failure, the broker will automatically publish the corresponding message. So essentially, this last will and testament feature fits perfectly with this project's heartbeat requirement. Finally, MQTT brokers like Mosquito include security features that will make it easier to implement the permanent and temporary password functionality required for this project. So those are some of the reasons why MQTT was the right choice for this project. Okay, so here's an overview of our system design. Because we're using MQTT, we will have a central broker that acts as an intermediary between the smart lock client and the mobile phone clients. Also, we'll be using two topics, control and status. So the control topic encompasses the lock and unlock functionality, and then the password activation and deactivation. So the mobile phone clients will be able to use the control topic to toggle the state of the lock, and then also the owner of the permanent password will be able to use the control topic to activate and deactivate a temporary password for a visitor. And one thing to note about temporary passwords is that the broker will also be able to automatically and independently disable the temporary password once the door is locked using it. That way the homeowner won't have to remember to do it. And this can kind of be thought of as an additional security feature. And then on the other hand, the status topic covers the messages that the smart lock sends to the mobile phone clients. And so this includes things like heartbeat, operation logs, operation results, and error messages. So the smart lock publishes to the status topic, publishes these messages to the status topic, and then the smart lock clients, the mobile phone clients, can subscribe to get updates about the state of the lock. And then finally, as we alluded to in the previous slide, we plan to manage the passwords using the broker because Mosquitto provides some built-in security features. Okay, so here's some implementation details for our system design. We have three main hardware components for this project: the central broker, the lock client, and the mobile phone client. So as mentioned before, we plan on using the Mosquitto library for the broker software. And this is a good choice for us because it comes with a lot of useful features that can help us complete the project requirements. And so for the broker hardware, we plan on using a Raspberry Pi. And using a Raspberry Pi makes sense for this project because the broker is essentially a command line application, so we really don't need a dedicated display for it. And then for the smart lock itself, it'll be implemented using an Arduino Uno microcontroller for the hardware. This made sense because I actually already own one. And then unfortunately, because the Uno doesn't actually come with the ability to communicate wirelessly, I had to purchase a Wi-Fi shield for this project. So that was one issue I had to address while researching the hardware. But like I said, since I already had one, it was still worth purchasing the additional component. And then one nice thing about the Arduino microcontrollers is that because they're so popular, there's a lot of documentation and an active community. So if you need help, it's not hard to find. And then also because people have already created multiple Arduino compatible open source MQTT clients. All we'll really have to do is pick one that best suits this project, and it shouldn't be too difficult to set up on the Uno. So the other two hardware components that are important for the Arduino portion of the project are the sensor and servo. So the servo will be connected to the Arduino and will be used to unlock and lock the deadbolt, similar to what was shown in the Hacker Shack project demo. And then, as we briefly touched on before, the sensor will be used to determine whether or not the door is actually open. And then finally, we needed a way to test a mobile phone client. So initially, I was considering making a custom mobile application, but later when researching this project, I found out that the company Adafruit actually has a free mobile application that supports a number of communication protocols, including MQTT and Bluetooth Low Energy. So this ended up being a good choice for us because we will be able to thoroughly test our design without having to worry about creating a mobile application from scratch. So here's what the implementation plan currently looks like. Keep in mind that this is subject to change, but as of right now, this is what we have. So Tyler will be primarily focused on software implementation, and I'll be mostly concerned with getting the hardware to work. And then Sweta will be working on conducting any additional research that we might need in order to improve our design. And then, so in terms of a general timeline, the main focus right now will be just to finish all of the individual assignments as early as possible, so that way we'll have enough time for testing and creating the demo at the end of the semester. So we're giving ourselves approximately 4 weeks to finish the individual assignments, and then about a week to test, and then finally a week to finish the demo and complete everything and conclude the project. So that concludes our presentation. Thanks for watching, and let us know if you have any questions.